So we'll start with the final lecture of Subhajit Goswami's mini course on GFF levels and percolation. So over to you, Subhajit.
Yeah, sorry. So today, since there have been a lot of contents already to digest, so I'll probably actually talk about more about the generic approach in this very recent result, and try to point out some connections with other areas of probability, other models in probability theory, etc. Then, by the way, am I audible properly? Or?
Yes, yes, you are audible.
Great. Okay, so let's talk about that. So this is a very recent result, just posted in the January, by me, Pierre Franco Severo. What it says is something quite interesting, and I'll tell you why. So as you see here, the main result is, again, you know the model, everything, so hopefully. So what it tells you is that it gives you the precise large deviation behavior of the truncated, okay, it's kind of the tail of the radius, the tail of the radius of the finite excursion cluster of the origin. So you can see the definition here. What it tells is that it's the probability that 0 is connected to the boundary of the ball of radius n, but it does so in a finite cluster. Okay, so in a sense, it's this event is same as the event that the cluster, okay, the exclusion cluster in the level set phi bigger than or equal to h of the origin has radius bigger than, in a sense, bigger than capital N, but strictly less than infinity. Okay. This type of function, as we'll see shortly in the next few slides, are related to the kind of probabilities that I talked to you about in the previous lectures, like 2-point function, like the connectivity function, or 2-point truncated function, where 2 points are connected but in a finite cluster, which are very important quantities to look at in statistical physics. So it's very closely related to that. So essentially what we're doing here is replacing 1 point with the boundary of a ball. And what it gives you is that the precise asymptotic behavior up to the principal exponential order as h, for all h that is not the critical point. Okay, at the critical point, of course, you will have hopefully power law decay. But why this is interesting is that this is a result for dimension 3, and this kind of result in this precision is difficult to obtain even for your classical models like Bernoulli percolation, let's say, even random cluster models. And so, and also here, this term h minus a star square is also very important because in this field, these exponents, they are somehow related to the so-called near critical exponents. Okay, not exactly so, because we are not really we're taking a limit in a large ball limit, but in a sense, this is kind of related to, for those who know, like the correlation length. So here it says that kind of, if you think about it, like the correlation length diverges as 1 over distance from the critical parameter squared. Another important thing is that you see this is also assume that this kind of connection probabilities, okay, they behave when they're very near h star. Okay, these prefactors should behave similarly. Okay, it doesn't matter which side you're off critical or subcritical or supercritical. They should behave similarly, and that's also it's evident from here that you see we're not taking, it's not like subcritical or supercritical. As long as you're not at the critical point itself, you have a behavior which is symmetric with respect to a star in H. Okay, now what happens in dimension higher than that? And you will see a drop in the level of precision, but nevertheless it's not known. It is not known before. well, it was known in the subcritical regime, but not for the supercritical regime, because, you know, these kind of events are always difficult, a bit more difficult to deal with, because you have to deal with. So when you're in the subcritical regime, that when you don't have an infinite cluster, this event doesn't cause you any trouble at all, because this is just empty, right? Because you don't have an infinite cluster, so you're just left with the connection event in the subcritical regime. So there, this kind of upper bound is easy to obtain. Okay, not easy, of course, but it was obtained in dimension 4 and higher for this kind of models. It becomes much more difficult when you put this one condition, which becomes relevant when you're in the supercritical regime. So you have to deal with an increasing and decreasing event at the same time. That throws up many challenges in your way. Okay, but here you see the rate is exponential, whereas here it is n over log. If you take it to the other side, it's n over log n. Okay, which is not the case again in Bernoulli percolation. So I don't know actually if there is a problem on my side, but I'm hearing a lot of ringing sound, but probably
yeah, so these are for joining. So maybe you can stop that joining sound if you can, editing.
Okay. Shall I go on?
Yeah, please go ahead.
Okay. Okay. So the first thing that should catch your attention is that this remarkable drop in precision, and of course the rate of this exponential rate based on this dimension, and I'll come to that very shortly. But let me first just give you a brief overview of about what other quantities can you infer about from this type of bound. One bound is the so-called 2 Worms event. So let me draw a picture again. It's always better. So I think I can go there. So right, let me use black, I think. So this event is something like this. Here you go. So let's say, let's see what the definition that I'm using here. Okay, Bn and B2n, that's good. So let's say this radius is 2n, and this radius is n. Okay, so it's a twice. It's this our standard setup. Like we're considering annuli with aspect ratio 2, and let's consider this event that you have 2 crossings from this inner box to the outer box, and they're in a disjoint cluster. So something like there is a disjoint, there is a dual surface separating. Okay, so that's the 2 arms event. That's what we call the. So that's what we call the. What you see here. 2 arms and H. So everything here that you see at level bigger than or equal to H. Okay. So that's this event, and this event is also extremely important, and they're in this same kind of class of events where basically what we want to say that whether 2 big clusters, 2 macroscopic clusters can exist. So these are all versions of local uniqueness. Okay, you should keep that in your mind. This essentially, so this makes sense, as you'll see here. This makes sense only in the case H is less than H bar. And recall, this H bar is the threshold which demarcates the strongly percolative regime. So below H bar, you have a unique infinite cluster. And from what we learned in the last 2 lectures is that now we have that this H bar actually equals H star. Okay, so it's same as a critical value, but exactly and essentially what they will be using here is basically the property of H bound. Okay, so this is all in this class of events, which is this local uniqueness in a sense. It's a kind of the finite volume version of uniqueness. So essentially, what you were saying is that whether you can have two macroscopic clusters, which is like local lots of disturbance. Sorry, extremely sorry for that. Okay, what you have is, okay, so these are all, so you have two large clusters, macroscopic clusters, which you can think of as kind of like finite volume analogs of your infinite clusters, and you ask whether they can coexist without being connected to each other, okay? So in infinite volume, they would be kind of like, whether you have two infinite clusters. The difference being that here, actually, you get much more quantitative picture, and it gives you a very good hold on the local geometry. So that's why these events are very important, are also very useful to construct other events. So how do we get a bound, similar bound on this event from what we learned there? Well, there is this result by Snitman. There is this result by Snitman in 2015, where he showed that if H is less than H bar, then the disconnection event, so it's basically the event that this annuli is disconnected. So you don't have any connection. You don't have any such rate connection connecting these two boxes. Okay. This event has a large deviation rate, which is very, very high, like n to the power of minus d minus 2. Okay. Sorry, my phone was creating a lot of problems. Anyways, forget that. Okay, so this is very high. So for example, if you look at dimensions d bigger than or equal to 3, when dimension d equals 3, this is like an exponential rate. And in dimensions higher than that, it's super exponential.
Sorry, Subhajit, just to interrupt. So it is n to the minus d minus 2 or n to the d minus 2? Because you're looking at the log, right? So if n to the minus 2,
right. Sorry. Yes, that's right. That's very good. Thanks for that. So this is definitely not true. This is minus n to the power d minus 2. Of course, that doesn't make sense because thanks for that. Yeah. This is the thing. So the minus sign was misplaced. Yeah. So that's why it's so big. Of course, if this is the case, then actually it's very close to 1, 0. Okay. So now if you combine that with the bound that we had now, it would immediately give you, for all the dimensions, actually, the corresponding bound for 2-arms event as well. Why? Well, so what did we learn from this event? So it says that you're connected to the boundary, but you're not connected to the infinite cluster has this large deviation bound, which is follow a behavior like that. Now let's look at this. So suppose what I have here is, I know by Snitman, I have a connection to infinity greater than or equal to h. This is by Snitman. Okay, so this cost me a probability like e to the power 1 minus e to the power minus some c times n to the power d minus 2. Okay, fine. But at the same time, if there has, so this connection is already there. Now at the same time, if there is to be another path, okay, let's say, so which connects this inner box, which connect actually, okay, sorry, let me do it in this way. So let's not go let's not go all the way up to infinity. Sorry, so let me do that because that would give me some problem. Sorry. Anyways, okay, So what Snellman tells you is that this event that you see here, this event, so this one got disconnected, let's say this one, okay, this one by Snellman, it gives me that, well, you're connected to the twice bigger boundary with a very good probability. Now, if there is another path, another arm like that, that connects to the boundary of the bigger box, okay, but it doesn't connect to, let's say, this one, okay, I know that the probability of doing that by my bound on this kind of event satisfies, this kind of large distribution behavior, that e to the power minus n over log n times this, okay. Then actually what you can do, you can again use Snellman bound to show that, well, if that is the case, because the fact that you are coming all the way up to here, and so it's okay. I think I messed up again. Just give me a moment. So, right. So if this bound is going all the way up to infinity, then if you don't connect to, no, I think this is correct. What I was doing is correct. Sorry for this confusion. Yeah, you go all the way up to infinity. Okay, so you do that. If you do that, then the thing is that, well, the fact that you will not connect this event, that you'll have another arm which will not connect to this one, okay, would be same as saying, so this is equivalent to saying that you'll have a connection that does not connect to infinity, okay, that's the fact. But we know by our bound on the bound on this event that, okay, the probability of having connected to distance n but not connecting to infinity has this kind of behavior. And since n over log n, of course, n over log n is is quite big compared to n in dimension. This is for dimension 3, and in a higher dimension, of course, n is so n to the power n is definitely bigger than n to the power d minus 2. For d is bigger than or equal to 4. This error that you're seeing here is a negligible, so this will be the dominating terms, okay. So that's kind of the idea, that why we can transport these bounds to say that similar bounds for two arms event as well, okay. And similarly, what you can do is that the proof, if you follow through the proof, you can get another very interesting consequence, which is also quite rare in this field to obtain easily, is that if you look at this truncated connectivity function, which if you recall, is the same as 2 points are connected, 2 faraway points are connected, but through a finite cluster, okay? So they don't connect to infinity. And we said that, okay, we proved already that this decays straight exponentially. But the bound that I just said, okay, it basically immediately gives you that, if you're this point, one point is origin, let's say, or for that matter x, and the other point is basically x plus something along the coordinate, one of the coordinate axis, okay. So it's if you're going in the axis aligned directions, then the same bound also hold, okay. There is not much surprising in that, but what is surprising is that you can actually modify this proof to obtain that it's not only for any given axis aligned direction, you can do it for all directions, okay. There is an isotropy, and if you're aware of this kind of things, you'll see that getting things for axis aligned directions is quite easy, sometimes easier, because you have several things aiding you, subadditivity. Although submultiplicativity will not aid you here, okay. That actually aids you to get results which is exponential. But here you have a strict n over log n, right? So that doesn't help. But in any case, going from there to every direction, okay, that's difficult usually, because your lattice simply doesn't possess that much symmetry. But here it's true, and the reason is basically again the simple fact that the quantities, the way actually you obtain these bounds are basically from scaling limits of random walks as boundary motions, which is isotropic. Okay, So you also have that. Although we don't prove it in our paper, but we give enough evidence because it requires some technical maneuvers. But we give enough evidence to believe that that's the case. Okay, so that's about the result. Now, let's go slowly into the proofs. Let's talk about other parts. How actually, why actually you see this kind of discrepancy in the strength of the results. And that has to do with the following fact. So let me first state it out, and then let me try to explain to you in a bit more detail. So this is to do with the fact that if you imagine, if you adopt, so away from the critical point, okay, your finite clusters, okay, if you want to go far beyond, your finite clusters essentially would look like a line, okay, because it's very difficult to, so for example, in the subcritical regime, it will be very difficult, let's say, to go from one point to another point, okay, to stretch that far, and that to do that, in a very fat way, because making a big cluster on the way out. It would mostly be like a thin set rather, and I'll show you that this kind of captures the right picture. So it makes more sense for it to do that just by creating one, kind of like a path connecting the 2 points. Okay. And similarly, when you're in the supercritical regime, again, going that far, but at the same time refusing to connect to infinity, that's also actually very costly. Okay, if you really gather a lot of points in your set, in your connected set, it would be easier actually to keep a low profile and follow some kind of like a thin path to travel to your destination. Okay, so that's kind of the idea. And how does this intuition lead to this kind of bounds that you see? And this has to do with the following thing. So if you imagine that like a line, so this is to do with the fact that how visible are these sets from the point of view of a random walk starting far away. Okay, I'll make them more precise. So let me first give you the numbers from where it is coming. So there is a quantity called capacity. I think you all know about capacity in some form, and I think those all coincide. And I'll start with the probabilistic description and slowly probably bridge all the gaps. But anyways, so what it tells you is that in dimension 3, if you just look at this line of length n, okay, so it's like 0 n, okay, that's it. Its capacity is n over log n. It varies like pi over 3 times n over log n, okay? And now probably you can try to start to relate how this, this factor is coming in both of this way. So so this log of n over log n, if you take it to the other side, something, what is the reason behind the appearance of this mysterious pi? Whereas in dimension 4 and higher, this is just captured linear. Okay, it goes linearly. And this is a very interesting consequence. So let me just state it out. So this actually bounds imply that if you take an infinite line in dimension 3, in Z3, this will be a recurrent set, okay, for the random walk. What do you mean by recurrent set? Remember, the random walk is transient, okay, in Z3, because it goes out. But it will be a recurrent set for this random walk. What means that the random walk will visit this line, any infinite line, infinitely often, okay? And this actually follows by this Wiener's criterion from this bound, okay? And similarly here, if you do the same thing for dimension 4 and higher, you'll see that it does. So let me actually give you this criterion. I think that would be nice to see anyways, as an aside. So this is called, quaternion. So it's kind of a extension of, you can think of like Levy's criterion for determining whether a set point is recurrent or not. So let's say, well, you can generalize it to any transitive props, but let me just state it out for ZD. So let's say you have V intersected with so V is a subset of ZD. Then V, by the way, you can actually follow it by ergodicity argument that any set, any subset is either a recurrent set or a transient set. So either, it's kind of a 0-1 law. So either the random walk hits it finally many times with probability 1, or it hits it infinitely often with probability 1. Okay, so V is recurrent if and only if this holds. The capacity of V, let's say, intersected with the annulus of radius 2 to the power k. So it's the annulus between the balls of radius 2 to the power k and 2 to the power k minus 1. Okay, divided by 2 to the power k times t minus 2. This comes from the Green's function. Okay, k is bigger than or equal to 1 is infinity. Okay, that's the condition. So if you just plug in this number here, I mean, you'll immediately see for dimension 3 is just 2 to the power k. So what do you have here? So this will, if you take a line and intersect it between these two balls, you'll get a line of length 2 to the power k. So you will have a 2 to the power k up here. This will this there. You have a 1 over k. So the sum of 1 over k is infinite. So it's divergent. So it's a recurrent set. Whereas here, well, you have too much, right? Because you have a kind of like a super exponential growth here. So you still get a geometric series, which is a finite sum. Okay. If you have any questions, you can ask me here. Okay. We'll come to more, close enough calculations of this capacity. But let's see. Let's look at it a bit more closely. So let me first give you a more probabilistic description of this capacity. What are these all about? By the way, these are also very crucial, this kind of equilibrium measures, as I'm going to talk to you about, from which whose total mass is the capacity. They're very crucial for defining random interlacing models that I talked about in my first lecture. Okay, so here is some notation. We use Px, P sub x, to denote the law of the discrete time symmetric simple random walk on the lattice starting at the point x. And let's take set U, and I'm defining first a more general setup, but we'll mostly be concerned about U as a whole lattice. So K is a finite subset of U, which is a subset of ZD. So U is kind of like outside which you kill the random walk. Okay, so this is, so let me introduce the equilibrium measure of K relative to U, which is basically the probability that X hits. Now, what do I mean by hits? So let me just write it here. Hits mean comes back. Comes back. It means that you don't count the initial point, okay? Because you see, it's supported, the measure is supported on K, the boundary of K. And boundary, I mean the inner boundary, okay? So the points that are in your set and that are adjacent to some points outside. So of course, if you can consider the initial time point, then of course this is always 1 and of no use to us. It means that it comes back. So in time bigger than or equal to 1, this is kind of the return time. So it hits K before U exit U. Okay, so if U is ZD, is just the probability that you come back to K for transient random walks. That is because, of course, if you're in a recurrent regime, that's why transience is so important. Because if you're in a recurrent regime and U is the full graph, well, then you always come back. This probability again is 1. Again, it's not very interesting. Only in the transient regime, there is a positive probability that you run off to infinity before coming back to K, because your set's a transient. Okay. So that's why actually, to make sense of it in a generic setup, we introduce this set U. So our set which you kill, so that this probability is always non-trivial. I mean, when U is finite. Okay, or in a proper subgraph of C2, let's say. So that's the equilibrium. Let's say this defines the equilibrium measure, and its total mass is called the capacity of K relative to U. Okay. And in this talk, I'll omit U whenever U is the full graph C. So let me talk about some properties of it, and this just emphasize this fact that why I said that what has this got to do with the visibility of a set with respect to random walk. So I already gave you one criterion, which is this one that gives you a proof. But let me also tell you something. I think some other characterizations of these measures should be useful to know, nevertheless. Okay, so here I go. So let me define. Sorry. HKY to be the limit that a random walk starting far away, okay, hits K for the first time at the point. So here I'm assuming, let's say, okay, the probability would be automatically 0 if Y is, from the definition, if Y doesn't belong to K, at Y. Now, of course, this is right. I mean, if I just stop here, let's say, if I just stop here, then the total mass of that would not be 1 if your random walk is transient, because there is a positive probability that you never actually come back, right? To make it a probability, I just have to condition that X hits K. Okay. Now, fact. This requires some work to prove, which I'm not going to prove. If you want, you can look at the book by classical book on intersection of random walks by Gregory Lawler, or you can try yourself. And you might probably guess it, what I'm going to write, but let me write it anyway. The normalized equilibrium measure of K, which is basically the equilibrium measure of K normalized by the total mass, which is the capacity. Okay, so as to make the total mass 1, to make it a probability measure, that's exactly equal. Okay, I should probably use, not to confuse, okay, let me just use something different here. Let me use Z, because I used, yeah, Z. Okay, so let's take some time to parse it. What it tells you is that, in a sense, the equilibrium measure, the normalized equilibrium measure at a point Z on the boundary of K is kind of like a, kind of this harmonic, like kind of like a points of control from infinity, if you think about it. Okay, so if a random walk coming from infinity, of course you have to normalize everything appropriately, and provided that it hits K, then what are the probabilities that it does so at a particular point. It's kind of like a Poisson on the point of view of infinity. So that's what this kind of tells you, and that's why it's important. Let me tell you another interesting fact, which is very important, for obtaining the bounds that I just mentioned to you. Fact 2, there are many formulations of capacity, but one is particularly useful for obtaining bounds, and this is the following. Let's see. So let's take a finite subset of the graph. By the way, this one again, you can replace ZD with general transitive graphs, and X belongs to ZD. Here I'm taking in the transient regime. Then this probability that the random walk hits this whole hitting time identity, that's why. The set K, okay, here X is not required to be on the K, of course. It's bounded above by capacity of K divided by the minimum Green's function evaluated from X and with respect to any other point of the K, and have a lower bound which is similar, except that you replace this minimum by a maximum. Why this is useful, or what does it tell you? Well, suppose the following picture. Let's say K is something like lying around here, and your point is this, X. From the point of view of this point, let's say the minimum and maximum distance, because of course we know that this GXY, you have a very precise asymptotic, right, in terms of the distance between X and Y. They vary like a Newtonian potential. So if the minimum and maximum distance are sort of comparable, okay, they're up to constants of each other, then what is this telling you is that, well, the probability that you hit K is essentially this approximate value of the Green's function times the capacity. Okay, so it's again another way of indicative that this is kind of like the capacity is indicative of the visibility of the random walk starting far away. Okay, fine. So let me go back to this one. Okay, so let me. So what I'll talk about, I'll not talk about this part. I'll talk about the most interesting part, which is dimension 3. And so in the first part, what I'll talk about the lower bound. Okay, how do you get a lower bound like this? And I'll talk about the easier one, which is the subcritical bound. But for the upper bound, I'll talk about the more difficult one, which is the supercritical bound. The reason for that is in the proof of lower bound, I want to emphasize some generic principles, so that I don't want to get into much technicalities, which to get in the way, which inevitably happens if you talk about supercritical. Whereas for the upper bound, it's important to see some underlying geometry concepts that we use. So that's the reason. Okay, so let's see. How do you prove a lower bound? And this kind of follows a generic way to prove, lower bounds in large division theory. So first, let me define this, kind of this family of events, which are kind of indexed or parameterized by a shift H, and I already talked about that. So let's say you have this event, okay, phi that 0 is connected to the boundary of a ball of radius n in above 0. And what you do, well, from this event, you can just shift it, right? You can just shift the field by h, any height, to get at the corresponding event at with respect to any other value of the height. So phi bigger than or equal to h. Okay, so there. This is also true for Bernoulli, right? I mean, if you can describe that in terms of the level sets of the uniform underlying uniform random variables, you can just fix one particular level and obtain the others by shift of this. But what is the usefulness of that? This comes from this generic entropic lower bound, and I'll tell you why this name, what this name entropy comes from. So let's look at, for your purpose, forget UN, okay? So this is just to refer to the GFF killed outside, kind of GFF for the random walk killed outside UN. So recall that, we define, so there are many ways to define Gaussian free field. The way we defined is a Gaussian process, which is mean zero and covariance given by Green's function. So you can do that with the kill Green function. So the Green's function for the random walk kill outside a domain, okay? So this is called the Gaussian free field with the Riddhipratim boundary condition at UN, outside UN. Anyways, but don't bother about that. We're not talking about it. So forget this thing that it exists. So it's like, assume UN to be just like ZD. Okay. So let Kn be a sequence of subsets, okay, whose size will actually grow, as is encapsulated by this fact that the capacity is growing to infinity. Then, if you assume that in an interval I of the real line, the following holds, that for every h prime in that interval, the probability of this event, so n is an event like this, let's say described in terms of the level set at 0, okay? And what it tells you is that throughout this interval, okay, the shift, corresponding h prime shift of that event goes to 1. Okay, so it's a sequence of high probability events. Okay, it will be very clear soon, when I'll discuss what they are in my particular context. Then the following lower bound holds. Okay, that this log of the probability at h, okay, divided by the capacity, that is lower bounded by the distance between your current parameter value and this interval. Now, why should this look similar to the bounds that I presented to you? So imagine, let's look at that again. So what do you have here? Here you have this regime H, okay? So this interval, this number H, and here is the term which looks like a distance from, let's say, if H is, let's say, bigger than H star, if H is, let's say, bigger than H star, then D of H, okay, with minus infinity and H star is basically your, like H minus H star and so on and so forth. But the point is that if you are on one side, you look at, so if you are in this, for example, here, if you're in this subcritical regime, you look at the distance from the supercritical domain, okay, which gives you the correct thing. And this jumping back and forth is the most interesting part of this whole business. Okay, so this is the distance term, and you have a distance term square, which you see in this form, okay? So it's essentially telling you that. And this factor is explaining why, how to go from this pi over 3 that you see here, in the capacity, which comes in the denominator, as you see here, and this pi over 6 that you're seeing here. It's 1 over 2 times that, okay? So that basically explains to you the reason behind that, that prefactor. Okay, now let me show you how to do this. And keep in mind the thing that I just told you, that you have to jump in order to prove lower bound in the subcritical regime. It's quite interesting. You have to actually jump to the supercritical region. And that's why this notion of sharpness is very important, because what sharpness tell you, I mean, sharpness means this equality of critical parameters that I talked through the last 3 lectures, is that as soon as you go a bit to the other side of a critical value, you immediately find yourself in a strongly percolative or non-percolative regime, depending on which side you are, okay? And you can use this kind of these strong notions of connection or disconnection that come to your rescue and to give very good bounds. And we'll see right now how it works. Yeah. Okay. Again, and also if you think about it, why actually you have to consider h bar while actually you're trying to prove something for h bigger than h star. The reason is exactly the following. How do you prove a lower bound, right? How do you prove a lower bound on probability that you connect? Okay. So remember, for the subcritical regime, we don't care about this part. So we don't care about this part. This is automatically 0. We just want to obtain a lower bound on the probability that x and y are connected. You cannot definitely do this staying within your subcritical regime, right? Because their connection is hard. What you have to do somehow, you have to compare, so as to speak, a measure to a measure in the supercritical regime where this is typical, where this is actually very easy to connect, right? And that's exactly what this thing is telling you, that you look at a particular region. So this is the interval I, okay, which in our case would be, for example, when you are looking at the lower bound for connection probability in the subcritical regime, it would be the supercritical regime, because that's where you can connect. And that's why, you see, this is the event on which you would like to find lower bound, or on which you would like to prove a lower bound. And this probability is going to 1. So I'm looking for a regime where the connection is typical. And then essentially what will happen is that the lower bound on probability would just come from the comparison cost, that the price that you have to pay to compare to a different measure, to pretend that you're in a different value of h than the one you are actually at. And that is basically this cost. Okay, it will be very clear to you if it sounds gibberish, but that's kind of the idea. So let me talk about that. So again, you definitely remember this definition of h bar. I cannot mention enough. So you have an existence part, you have a uniqueness part, and so on and so forth. And although we'll just use the fact that it's h bar, but remember that we have now proved that h bar equals h star. Okay, so this is the regime when h is less than h bar, I have a connection, and I can glue the connections by virtue of uniqueness. Remember that we spent quite some time about that. Okay, so how to do that? Let's go over it quickly, because we are running out of time anyways. So what we're doing here is essentially we are taking this line, okay, from 0 to n, and taking an thickening of that, L thickening of that. Okay, something like this. So it's like you can think about, this line plus 0 to n cross 0 to the over d minus 1 plus BL, so as to speak. Okay, so if you do that, then what you do is you look at two faces centered at the point 0 and at the point n. So let me draw, I think it would be better to draw a better picture, but let me not waste time on that. But let's say here I have a picture, things like that. Okay, so let's say these are the two faces. And the event that we are interested in is the following, that whether, let me use orange, whether these two faces are connected by an open path in some h. Okay, we'll vary this fact in the current form. Okay, the width is taken here to be, we'll see actually, but forget about C1. C1 is same as this one. We'll see shortly why we take that, but don't bother about that. It's something which is very thin, polylog. We'll see why. Okay, now, how do you draw this crossing? Of course, you cannot do it at h. Okay, so instead what we'll do something different. We'll look at, as I said, we'll pretend that we're different value of h, which is h prime, which is below h bar, where actually this kind of, drawing connections is typical. Okay, and I want to be able to use this lower bound, this entropic lower bound. So I have to verify that, well, it is indeed typical, but you might have already guessed it. Why? but let me just tell you, this is basic idea is again this kind of notion of gluing. So what we require here is that I am requiring throughout, in all the boxes, in all the boxes that you can draw like this, I'm requiring all through them the existence of clusters like this, which I can do. So by virtue of this property, which we can assume to be true because of the definition of local uniqueness, right? So remember that I talked to you about how you can use these events to glue together these big clusters using this uniqueness repeatedly through adjacent clusters, okay, adjacent boxes. So that's exactly what we're doing there. Okay, we're now actually reaping benefits of that definition. So you're connecting them, and the reason actually we took the definition 2 over C1 is nothing but that 2 over C1 raised to this power gives you a super polynomial close probability, a probability that is super polynomially close to 1. So you have this orange big clusters, and you can actually also connect them. You can connect them using uniqueness. Okay, so you can make this kind of this connected this kind of rings of paths, this links of paths from the left to left, right? So this will give you a path connecting these two faces. Okay, this orange one that we are looking for here. Okay, so that proves basically kind of gives the idea why whenever you're in this strongly percolative regime that is below h bar, you connect with a high probability. Okay, so the first condition is satisfied. What is the second condition then? The second condition is, of course, that in order to get from there to this lower bound, this to get so h minus h bar squared I just explained to you, right? Because so as I explained to you that the distance between h and the appropriate interval I, which is basically to the left hand side of h bar, right? So this is this interval. That's basically h minus h bar whole square. So you have this. So it's sorry, used right. So you are here, h bar, which is equal to h star, and you are to the right of that supercritical region. So the distance between these two is just that. There is nothing mysterious in that. Half comes from the half that you see there, but when does this come from? Okay, so that, if you recall, is the capacity. Is this capacity of this region on which this events ANs are supported. Okay, now on which set is the event AN supported? Well, this is just supported on this thin tube. Now, as I told you, the capacity of line is like n over log n, pi over 3 times n over log n, right? So you might be tempted, okay, now that's there. Well, it's not really so, because you see, okay, great. Okay, what I was saying is that I don't know actually how much did I cover until this disruption took place. Okay, so I'm assuming that you heard me about. Okay, I'm assuming that I could come all the way up until here. So what I was talking about is that that we're going to pretend that we are a different parameter value, okay, which is in the region where you'd be able to connect or create these connections in a cheap way, so that this probabilities go to 1 as is required. And to do that, what we do is that we fully use this definition of local uniqueness. We consider this event, which I tried to draw here. I don't know if it makes sense. So, you just pave your tube through this adjacent cubes like this. And what you require through each of these tubes, in view of this, in view of the fact that you're below h bar, so you have a stage exponential high probability for local uniqueness, is that you can draw these connections, okay, these orange connections, which is written here as such, by gluing, by gluing components if necessary, as I pointed out earlier in previous talks. and also require uniqueness. So by which you can actually also link the adjacent clusters all along the way to create a connection between the two faces. Okay, so that's the idea. So this notion of local uniqueness allows you to do that, provided H prime is in this interval. Okay, so you have verified that the limit, these events are likely, very likely. So they occur with high probability. So that explains one part. Good. So now what explains? So that explains the H minus H bar square, right? Because I don't know if I talk about that, but because remember we are in this regime. So this lower bound involves the distance between H and I squared. And what is the distance between H and I? So H is in the subcritical regime, so it's bigger than H bar, which is equal to H star. And this area where my assumption, this assumption of this entropic lower bound holds, is the one where these probabilities go to 1. So this will be everything to the left of H bar. So hence this is the interval. So the distance being H minus H bar square. Okay, good. So the only part that is remaining is the explanation of this part. Okay, which, well, if you just remember what I told you, well, you can just say, okay, it's just from the capacity of the tube, capacity of the line that we just talked about. It's the pi over 3 times n over log n. Well, not so much, not immediately so. Why? Because you see here, what is the region? So what is the capacity we are looking at? Capacity of the region is a region on which the event is supported. Okay, so it's the Prudhoe, it's measurable relative to the Prudhoe, that's an r to the power kn. So it's supported. The event is supported to kn. So here, so that set would be this tube. Okay, this is my kn. Okay, but this kn is bigger than our line, so it will have a. So capacity is like a measure. Okay, it's a measure. So you see, you should think about it like that. So it's a the bigger the set. So although it's not really a measure, of course, because I don't think it's not like countably additive or anything finally additive for that matter, but it's somehow like a notion of content. So it's monotonic with respect to sets. So the bigger the set is, the more is the capacity. So this capacity can be very big, and that can actually mess up your bound, because if it's too big, that gives you a very bad lower bound. But it is a very nice consequence. So the properties of random walks actually in 3 dimension, and it uses Gamble's ring. The idea of Gamble's ring to argue that actually, even if you thicken it by a power n to the over delta, the capacity only increases by a very small number. Okay, so we're good with that, and we can send this delta to 0, because remember, well, we're basically thickening it by polylogarithmic width. So that's kind of the idea. So you jump over to a regime where you have strong connection probability. So you build your connection. So you create a witness of the event that you are trying to lower bound, which is connection, and then you pay for the fact that pretending that you're in a different regime than where you are, and the cost of that is given by what you see here, the distance from the area regime times the capacity which you estimate. Now let me quickly talk about how do you prove this entropic lower bound. And those who are familiar with large deviations immediately identify this, but this is not so much important to prove this, which you can prove easily as an exercise by Jensen's, but the meaning of it. So this tells you about this cost that you have to pay to pretend that you are at a different measure. Okay, so this what it tells you is that, you see, let's say you want to obtain a lower bound on probability of an event A. Okay, now what you have is that you have a different probability measure p tilde, let's say, on which p tilde is kind of typical. Okay, so p tilde is kind of close to 1. Okay, then the price that you have to pay is written here. Okay, is exponential in something which, if p tilde is close to 1, it's close to 1. times the relative entropy, hence the name entropic lower bound of H of P tilde over P, which is, yeah, as you see here, it's called the relative entropy. It's the expected value of the logarithm of the random negative density of P tilde with respect to P. Okay, again, proving it is a fun exercise, but what it tells you is that the way to obtain a lower bound, optimal way, would be to come up with a kind of a narrative, a story, which tells you that, well, how, if at all, it has to build connection, what would be the best way to do that? And the best way would be really to pretend that, that you are at a certain kind of optimal P tilde for which this kind of even becomes typical, and you pay the price for that. Okay, so how does it work for the Gaussian free field? And for the Gaussian free field, the thing is that you can actually readily check from the definition that, so what is P tilde, by the way? So P tilde is essentially, for our case, is nothing. It's nothing but the law. So P tilde would be a shift of the law of phi by some height or height profile. Okay, because what we are trying to do is that so we had one event. Let's say the level set at 0. We're trying to pretend that so let's say at H, we're trying to pretend that by shifting the height, we're at a different regime. Okay, so that's kind of the probability measures, the family of probability measures we're looking at. So for that kind of probability measures, the Cameron-Martin theorem tells you the random negative density takes this form. Okay, so E is basically the standard Drake-Cheiner product on the graph. So in this case would be 1 over 2D sum x, y, fx minus fy times gx minus gy. Okay. Okay. Now, then what it does to you, what it tells you is that then you can actually easily estimate. You can just do compute the. So this is again a zero mean Gaussian variable essentially. So the relative entropy boils down to the Dirichlet energy. Okay, the relative entropy cause that you are seeing is the Dirichlet energy. So what you have to do, you essentially have to minimize, okay, to obtain the optimal cost, to obtain the optimal lower bound in terms of this, because you like to obtain the minimum value of this to get the best lower bound. You have to optimize it, minimize it over all choices of finally separated function. Says that fkn equals, actually here is not 1, it would be something h minus h star. H minus the value by which you want to shift. So let's say H minus H bar plus epsilon. Okay, so recall that we are here H bar, we are at H, we are studying it at any point slightly below H bar. That's where actually the connection probabilities become trivial. Okay, so then actually what we should solve the Dirichlet problem with this boundary data plus epsilon, and so is basically correct, but let me just add it here. It's just scaling the two sides squared. Okay, so the minimum value that you can get by solving this Dirichlet problem is essentially the difference squared times the capacity of the set. Okay, this is one of the traditional formulation of the capacity. And hence, this leads you to this entropic lower bound that you see here. But this, as I told you, this idea is actually also useful in many other contexts. So you can keep it as one of the standard toolkit in your mind. Okay. Right. So let me quickly browse through the proof of the supercritical, which I cannot do justice on, but let me try my best. So here, the idea is something like the following. You don't have to parse this B given, but the main point is the following. Here, what you have to do is that the idea is something like this. Let's see. Sorry, actually, I could use that. I think, let me just do something, sorry. Okay. The idea would be that how to actually prove this. So remember what we have to prove. We have to prove something like this. So we have to prove that probability that 0 is connected to boundary phi bigger than or equal to h, but you are not connected to boundary, I'm sorry, not that, to infinity in phi bigger than or equal to h. That's one. So we want to obtain a lower bound on that. The idea is basically the following. The main problem here is that you see in this kind of in this entire topic of dependent percolation that dealing with decreasing increasing events at the same threshold is actually quite difficult. You have to usually allow some sprinting, some wiggle room. Okay, so achieving that is really hard thing to do. Anyways, but the main idea is something by this kind of Schneemann bound. We know that, let's say, what I'm giving a cheating proof, nevertheless, but still it will have some idea. Okay. First, I will have this fact that by Schneemann, so upper bound on the disconnection probability, I know with a very good probability, I will have a connection to infinity. Okay. And I can do that since my h is strictly less than h bar. Okay, I can take a value which is, let me write it properly. H is strictly less than h bar. I can take a different value, let's say, h plus some small epsilon. Okay, so that which is still less than h bar. So I have this number, this level set, slightly bigger height. Now, what I'd like to do is the following. How do I like to say that? Okay, the problem is that as you lower the height h, you can open up much more connections. That's the main problem. You see, uniqueness is not really a monotony even. I think that was clear from Tom's talk as well. So how do you actually prevent the, how do you actually ensure that if you open a new connection at a slightly lower height, let's say this one, let's say it's bigger than h, how do you make sure that they connect? Okay. The idea would be that what I can do will create a lot of surfaces around this point, such that every time, so whenever there is an orange path, it has to intersect to each of these surfaces. Now, what is the property of these surfaces? These surfaces are so-called good in many sense, one of which is that it allows you to perform this local flexibility that you usually get in Bernoulli percolation, that you can perform local surgeries to connect and draw things like that, gadgets like that. Two, they're all connected, okay? And by virtue of this same property, they will be all be connected to this red infinite cluster, okay? So the idea is that this orange path would find it extremely difficult to not manage to, to hit one of the, it will have to hit every blue subset. And whenever it hits one of the blue subset, the surface, there will be a finite price on, by virtue of the fact that the blue surfaces are good. So it means that you can perform some local surgeries. So every time I hit, I can perform a local surgery. Every time I hit, I perform a local surgery. So this gives you a positive probability of connecting. Okay. So imagine this, compare this to the argument that I sketched for slab percolation in the very beginning of the talk. Here in terms of slab, you have this kind of surfaces, which are arbitrary segments and which have very nice other properties. Okay, now what happens is that you are in kind of the similar picture where you have many encounters, and in order to miss this opportunity to connect, at every such encounter will cost you a positive probability. Okay, and that will be very costly to do. So in all of these layers. Okay, so if you kind of finally show, and which is actually kind of written here, that your number of layers is very big compared to the lower bound that you are aiming at, this exponent, right? Then what will happen is that you will, in order to miss this kind of all of these layers, you have to pay a price which is e to the power minus number of layers. Okay, so if that is very bigger than n over log n, then that's good. That's, you're done, right? Provided, so this doesn't bother you at all. This doesn't enter your lower bound, this doesn't bother so far as you're concerned with estimating the principal order, exponential order. So far as you can produce this picture, with the required probability. Okay, that it will be basically the correct probability, with the required capacity upper bound that you have. To do that is difficult. I cannot do that now. But the idea is that there is a notion of the fact that producing a picture with surfaces is very difficult. So what we do it, which is a nice idea in this work, is that we dualize this event. So you convert the problem of existence of such layers by the problem about paths. So you can ensure that. So I promise you I'll not take more than 5 minutes. Can I take that? Hello?
Yes, we started a bit late, so you can take 5 minutes.
Okay, yeah, okay, but I'll try my best to finish, but I just want to point it out. Okay, so what I do is like a picture idea. So there will be, what I want to show that, that there exists this blue layers, that sufficiently many such blue layers, which something girding you. And to show the existence of such is quite difficult usually. But as you have seen, it's quite easy to look at the dual of surface, which is the path. Okay, so we'll establish the existence of such layers by showing the existence of certain types of paths, which are easier to obtain. And so what will be the properties of these paths is essentially that there will be a blue set. There will be blue sets. Okay, these blue sets will have the property that they are good in a sense that locally, they have, they allow you to perform these local surgeries. They will have this local uniqueness, so that so these blue things will be defined in terms of coarse-grained lattice, okay, in terms of balls rather than points. So more correct picture would probably be something like this to look at. Okay, right. Anyways, so the second property would be some kind of this local uniqueness, so that if you have a connected surface formed by this good boxes here, they will form a connected surface. All these kind of properties have to be there, and the way we prove it is something like the following. So what we'll do is that, okay, instead of directly positing the existence of such surfaces, we'll first consider the set of such blue regions, okay? And we'll say that any path that connects the inner box to the outer box intersects at least a good number of them. So here is a version of the lemma. So this is a kind of a very generic fact I think we can just look at. So here, this is kind of a generic statement. This is no probability here. So here is a clean way. So we say that, if you have two point sets, U1, U2, we say that U1 is surrounded by U2, in the sense that U1 is shielded by U2, if U2 blocks U1 from connected to infinity, okay? So in order to go from U1 to infinity, you have to go through U2. So here is this thing, this lemma, that, so what I want is that I have some, right. So this will not be S, this will be V, this will be U. But anyways, so I want to create a bunch of surfaces, okay, using the points in some set sigma, which is my good set, okay. For that, all I have to ensure is that every path connecting U to the boundary intersects sigma in substantially many points, because essentially what you have to then bound is that essentially what you have to count the number of back paths which doesn't have this property, and that turns out to be doable. And by if you can think of like Pell's type argument, kind of standard counting arguments. But the nice part is, why actually you get such weird bonds? How does the capacity come into the picture in this context? Well, this comes from the energy part. So remember, when we do, so forget about everything and don't try to parse everything. I'll just tell you what to get from here. So you remember when we proved that the percolation threshold PC is 1/degree, okay? We count the number of paths, which is exponential in length, and the energy, which is the cost of such path open. So that's the energy part. Here, the energy part is different. And the energy part would be basically governed in dimension 3 by the capacity of some kind of thickening of this path. So this is given by this result by Schramm and uses some deeper properties of Gaussian variables. But anyways, so that's the idea. That's how the capacity comes in the upper bound. But the main take-home picture is that you have a problem involving surfaces. You dualize that, convert it to a problem of paths, and then you run your energy entropy argument. But of course, then you have to be able to estimate the energy and entropy. But that's hopefully you can do it easier way than counting surfaces in the first place. Yeah. Okay. So sorry for all the so many disruptive things that happened throughout the talk. But I don't know actually how much good job did I do. I was not very happy with my today's talk because it was disrupted so many times. But anyways, probably I'll not waste any more time. Thank you.